Hello everyone. Today we are going to talk about legal projects and how to survive them, basically. At first, let's, sorry. Just a couple of words about me. My name is Yuri. I work at PBS Studio as a C++ developer. And if you don't know, we are developing a static analyzer for C, C++, primarily. Also, we have C# and Java. Well, let's go and begin the actual, thing. So what we are going to talk about is the world has changed, as you see here. And the change was in a way that code in projects became larger. The projects grew, and with the size, usually complexity also grows. So what happened is, well, it's kind of obvious. The longer your project lives, the more code it accumulates, the more changes go into it. And of course, teams of different people tend to work on, well, large projects, let's call it that. It's not your average pet project, although I think there might be different contributors. Okay. And they write code, and code goes over code. It's like in geology, different layers of soil go one over the other. And this comes undetected. I'm speaking from experience here because I'm working in one large project which has lived long, and it's kind of funny to look into code which was written like years ago. So, well, basically it looks like this. I don't know about your experience. What I observe here is, well, something similar to this picture. Okay, so you might ask at this point, so yeah, Cap, thanks. But what do you want to say? It's kind of obvious. Let's begin with some statistics, just to show you my point, kind of. As Mr. Twain said, there are three kinds of lies, and statistics is the worst of them, basically. So let's look at some statistics, shall we? The Linux kernel, when it began, it wasn't tiny, of course, but it was manageable. But now, as you can see, the amount of code there increased dramatically. Same goes for enterprise software like Photoshop. Well, I think it's quite an increase in the amount of code. And if you know what this is, well, you might be surprised, you might not be surprised, but this thing, even this thing has about 35,000 lines of code. So yeah, we are talking about legacy today and how to deal with it. Let's start from legacy. So what it is I think everyone knows, it's some code you inherit from previous generations of people who wrote your software. And if you look at this definition from Wikipedia, I don't think it looks very scary, but in practice, sometimes, not all the time, but sometimes you might see something like that. If you go to some old code, and when you come to a project, it might look like this. Yes, so these pictures are from Warhammer. Just a side note, I'm a fan of the universe, kind of, so I decided to keep them here. So this monolith on the background, it's not actually a monolith because it consists of some parts. And if you look closer, you might see a structure like this. And some parts of this structure are very interesting. So you might have some code from the legendary guy who was with the project at the beginning, or not a guy. Uh, those people, so-called bus factors, they tend to leave a lot of code behind and let other people deal with it, basically, when they move on somewhere. You might find a third-party library which is there just because, and which is no longer maintained. What else? Of course, to make this structure holding, you might find a lot of, supports, let's say. Let's put it like that. And of course, there is a big module. The whole software is built around, and it's leaking abstractions as crazy. This is what I'm fighting with kind of right now in my development process. And we are talking about C++ primarily here. So, we like to reinvent wheels and make bicycles and stuff like that. It's kind of how we live and how we like it. So, yeah. I saw a whole implementation of the standard library as in STL in our project. And yeah, sometimes you have to make dirty fixes and leave a to-do comment just to, return to it later and make a proper fix, because the dirty fix is dirty. And here at the very top, you might have something which is modern and maybe maintainable. Well, needless to say, all those, the lower you go there in the structure, the more difficult it may be to maintain the code, because standards change and compilers change, and old code sometimes is lagging behind modern way of writing. Okay, how do people usually deal with it? Well, we have proven methods like code reviews, unit tests. Compilers help us with warnings, and if you set a flag to treat warnings as errors, your build will never be complete if you have them, so that's useful. But I'm about to say something which may put this kind of look at your face, because I'm about to say that those methods, even though they're good, they're not always working, and we need serious help in order to overcome problems which come with them. So what am I talking about is kind of like this. If you look at this code, I'll just give you a moment to try and find where it went wrong. Well, I obviously don't have any feedback, so I'll just show you. So here, we are obviously checking some gamepad input from a thumbstick, and it has two axes, and here, because of the copy-paste, only one of them was checked. This code is from an open source project. I won't call names here, so it's just an open source project. And this code passed, I hope it had some code review and tests, and it passed into production. So let's take a look at a different example. The next one will be kind of funny. Well, at a first glance, looks okay. Well, nothing here is really, really bad or suspicious. at a first glance, but if you noticed it, you have sharp eyes because the return statement here doesn't have a semicolon. And what this code ends up doing is it clears the map and then returns, well, when this condition, when the condition is in the if statement is met, it clears the map and returns. And since the map is passed here as a reference, well, actually it's a vector, probably it's not an intended way to do things in this code. Okay. Now, when I first saw this, I went kind of like, oh, can you do that? Can you really return something from a void function? Well, turns out, yeah, you can. If you make a small example like this and you look at Godbolt, which is a great site, by the way, you will see that it compiles successfully, and that is Clan. I believe it was, yes, it was the trunk version. So this code works. Nothing will break if you do it. And yeah, my surprise was that you could return something from a void function, but turns out, yes, it's permitted by the standards, and it just executes whatever you pass to the return statement, and it just goes away from the function. And these are things, tiny mistakes that you can do, and they can make your life difficult on a large scale. And they can lie dormant there for even years before they, crawl out and ruin your day. So when this happens, when eventually a potential bug becomes a real bug, well, obviously you want to hunt it, and here comes the fun part, because when you begin hunting a bug, well, it might look like that. It's small. You think you understand how it works, how to fix it. Oh, it's kind of cute, maybe. But what usually happens is you go there, you hit some old layer of code which you didn't even know was there, and you see something like that written, in the old style without any classes or without any even good type defs. Like you see a lot of ints and loops and ifs, and it's all like tangled. And you start looking like that probably. Well, I know I do start looking like that when I go to some really obscure parts of our code. And the bug, which at the beginning was tiny and kind of benign, it becomes like, it starts looking like that most of the time. Well, at least in my experience. And you spend the whole day with a debugger. So what results from that? If you leave a lot of old code unchecked and you keep adding and adding and adding things to it, well, usually the more code you get, the longer the debugging gets. And, when you need to add that small extra support to keep it from falling, it may be difficult, and you will probably need to add, you will probably need to cut some corners here and there when you're dealing with an existing code base. Yeah, you often have to make dirty fixes, because if you go deeper and touch some underlying mechanisms under some feature, you might break something in a surprising place. And well, there's an upside to that. You may feel like that, and about the value of those long and tedious debug sessions is when you finally figure it out. You go like, yeah, I'm cool. Okay, so let's digress a little bit. I found this quote one day, and I think it really shows the problem we have in the modern days of development, and that is that we like to write a lot of code, and everyone's guilty of that. I'm guilty of that. I think, well, I think every person who writes code likes to write code and adds more and more of it. And here in this digression, I want to tell you a little story. It won't be long, but it happened to me when I was working at a different company. And I decided to make it into a kind of a play. So the things happened in one company, which I will not name again. They had a development team and a really big project, which was built from an idea to a huge system, and obviously it was a mess. And one day there came a need to support a new technology, a completely new one, which didn't even exist before that. So they decided, they started to work on it, and something like that actually happened when the discussion went on. So the developers insisted that, okay, the system is difficult to maintain. We need to do it. We need to do something to ease our lives. And this was going on and on, but they ended up making new features instead of maintaining and refactoring old code. And one day, when this great new feature came along, it turned out that it was almost impossible to implement it. You may argue that the architecture was bad, and it probably was, but the fact is they were unable to do that. So the project essentially died trying to cope with all the changes necessary. And what happened next, you will probably guess. They scratched it, and they decided to write it from scratch, and it was painful. It lasted about 3 or 4 months, and people were working without rest, basically. They lost some good developers because of that, who decided to leave the company after. And the thing went boom, obviously, but it ended well. At least it ended well because the new version was reworked completely and was working fine. So it may sound scary. So is there any way to prevent it? Well, yeah, there are ways to prevent it, but we should understand that it will happen unless you are in some perfect universe. And the longer your project lives, the more its complexity increases, the more problems or potential problems you will have with it. And that's why we need to catch this issue at early stages and start introducing some techniques to not allow things to go amiss. So, well, what can we do here? I think refactoring is a big part. rewriting some code which is not, well, which you think is not designed well enough, is a big thing which can help you. And what we want to do is to let machines do the most tedious parts of this work. Well, ideally, I would argue that a code review should be, for the most part, done by a machine, but this would require an AI, which we don't have at the moment, sadly. And this brings us to this famous DevOps cycle, or when you do tests during development, you release often so your users can report any bugs which fell through the cracks. But this picture itself is also not enough, because the test stage of this is your, standard issue unit tests, which people can forget to write, which can cover a tiny part of the software, not the entire thing, and there are problems with them. And also, the more complex your software gets, the more security loopholes might be in it. So security is something you also have to consider. It's kind of becoming a hot topic, I mean, in the industry of static analysis, and static analysis is all about security. Well, at least everyone claims that security is one of the priorities. But if you look at it from the coding standpoint, what a security issue is, it's just a programming error. In many cases, it is something, some logic error or design flaw, but in many cases, it's just a silly mistake which could have been prevented on an early stage of the development, and it could have been kept from leaking into a release and production and to users. Well, of course, prevention is always better than cure, so we want to deal with any potential issues as early as possible. Ideally, before even making a commit or a pull request or something, before it gets to the main repo. Well, in general, because people get tired, people have limited attention spans, we want machines to do most of the things. Why I'm talking about security? Because security, if you do security testing, it will eliminate a lot of other bugs, which are not necessarily security defects or vulnerabilities. So let's look at our wonderful DevOps cycle again, and we'll add one tiny little bit here, and that is this little gear in the middle, monitoring and analytics. This is what we need to have in our pipelines, and it should be constantly working as a part of the build process. In addition to tests, we need to also monitor and analyze the code for on a different level. And for that, we have, well, basically we have two categories of tools. We have dynamic analyzers or sanitizers. Probably you use them at some point. And we have static analyzers. Let's talk about each group specifically. And first, we will look at dynamic analysis. Well, this is dynamic, but it's not what I meant. The list here is kind of arbitrary because debuggers and profilers are not, strictly speaking, any dynamic analyzers. Profilers maybe are, but debuggers are here just because they are the organic part of the whole process of runtime monitoring anything. And sanitizers are very useful because in many cases they can catch runtime issues which fell through compiler warnings, and they went safely by some static analyzer, and they got into the code anyway, and they were built. But at runtime, something bad happened, like the example we'll look at next. So what dynamic analyzers are really good at is catching issues at runtime. So let's take a look at this code. I know it's silly. It's not meant to be used anywhere except for this demo, but what happens here is we allocate some memory, we free it, and we access the freed deallocated memory. Things like that happen in production code, and people sometimes overlook them. If you run a sanitizer and let it work overnight with your software, it will catch it. This part here and the way it's reported, it's kind of unreadable. This is from asin, and well, basically it will point out where you accessed memory which shouldn't have been accessed, and where your code went kind of crazy. Dynamic analyzers, they have their set of limitations, and the most notable of those limitations is that you need to run them with some unit tests or on some data set for your application, and this data you feed to your application while it's being tested, it needs to be formed in a way that will allow your program to cover most of its code. Well, not all, probably, but most of it. Dynamic analyzers are good at, they have good reliability because they don't issue false positives at all. Basically, if they find something, it's there, it's a bug. The next group of tools is where I come in usually. It's static analysis, and what it does, it looks at your code and tries to figure out, well, where it went wrong. So, the analogy I always use about static analysis, it's code review done by a machine. So code review by a human is good. It's great. It lets you share ideas, but there are some reasons that prevent you from actually doing it. You may do it in a lazy way. You may just skip it entirely because you're tired and things like that. Well, so at this stage, I think a robot could do better, something like that. It won't be happy about this proposition, but who cares? It's a robot, right? Let's come back to our previous examples and figure out what a static analyzer can do. So in this case, the message here is from our analyzer, but you could just take any analyzer which is aware of copy-paste issues, and I think it will find it. So here it just says, okay, you have identical expressions, something probably went wrong, and it's up to you to decide what to do with them. Well, here, again, such tools are able to detect this situation just by looking at your code, whereas a human might just, skim over this function and miss this return without the semicolon, especially if there are a lot of blocks like that. So just a quick recap, dynamic analyzers are good with tests at runtime, and I recommend using them all the time at your nightly build, check along with all other tests. They will allow you to catch runtime errors, which don't necessarily crash anything. And static analyzers are like code review. They are useful if you use them after any significant change in your code base. Like if you write at least the parts of some feature, if your code goes into your repo, it's useful to check it for new defects and potential defects which you may have overlooked. And if compared to each other, they look kind of like this. Dynamic analysis is very precise. It will hunt down any errors which are actually there, provided your test data allows you to cover everything. But it's slow. Sanitizers tend to slow runtime significantly because they need to do a bunch of stuff like instrumenting code and injecting their own code into yours and executing a lot of additional functions. Static analysis, on the other hand, is, well, it's fast. All it needs to do is just have your source code, but it can backfire because, static analyzers do a lot of false positives, especially on some code which was there for a while and was never checked. Okay, so those two groups of tools will decrease your pain significantly during the development process, and they will help you make your project more maintainable, hopefully, in the future. So how can we use them? Well, you can use them just in your CI system, just add steps for them and let them run. Or you can use quality assurance platforms like SonarQube, for example. If you heard about SonarQube, I don't need to tell you what it is. But if you didn't hear about it, it's a web-based solution which allows you to integrate different tools into your pipeline and run this entire setup as a step. And it can it allows you to set up quality gates in a flexible way, and you can fail your builds if it finds anything suspicious. So this is again from Wikipedia. I think it's boring, so let's just summarize what it can do. It's an open source solution, although they have paid components there. If it can't do something out of the box, you can usually add it because it's highly configurable. Well, all you need to do usually is set it up once, configure your quality gates, and let it just sit there in your CI as a part of the build process, and it will provide, well, great reports to you with charts and stuff like that. That's all we love, you know. So why use it? Well, because it makes your life easier. For example, here is a screenshot from SonarQube's interface. It can check out your sources from your repo. It can check them during the build. It will show you where exactly errors occurred, what types of error occurred, and it incorporates static analysis. You can use its own analyzer. You can use third-party tools. You can use dynamic analyzers. It can parse output of many different things and present it in this nice readable way. Well, this is an example of code smells. It was able to find in my test code, which is messy on purpose. Here is an example of what an output from a sanitizer can look like. Here we have fault grind, I believe, yeah, fault grind. And it's much more readable and understandable than the thing I showed you earlier from the ASON, because that was plain text and not parsed, and here the system showed you showed it to you in a readable way. And it has reports and things like that, so it's good. It's a good platform. Well, and it allows you to find things which are not so good and kill them in your project after the build. Well, it's all good and shiny, but what to do if you have a really, really old code base and you want to start introducing those tools? Because what I said, well, prior to that, it kind of is related to new code. You know, when you are developing a project, you just begin to develop it. If you introduce those tools early, it will help you alleviate a lot of pain later. But what if you have a really, really old project? Suppose you have a static analyzer and you first run it on your code. It's going to be painful because the code, which was never under surveillance of a static analyzer, it will contain a lot of things the tool won't like, most likely. You will get a lot of warnings. You will get something like that, most likely. Yeah, and it might be messy. You might be lucky. It might not be messy, but practice shows it will probably be messy. So why is that? Because why is old code contains a lot of noise? Well, because it has many typos and small things like that, which were overlooked and accumulated. So yeah, the old code is noisy in terms of warnings, even if it's well tested and really polished. It might be noisy, and the proportion of noise to useful warnings will be in favor of noise if your code is of good quality. Well, if it's polished, because you have polished it by debugging it painfully over the years, and only small things left. Just a little disclaimer: it's not a problem of tools. All static analyzers will reduce noise one way or another. It's just the way they work, because they use a lot of heuristics and stuff like that. Well, what can you do to reduce that noise? Well, if you have old code and you know it's not going anywhere, you know it's tested, and you just don't want to dive into it, you just can suppress everything. It's kind of, it may sound like a bad idea, but it's not. You don't want to see a lot of distracting noise. You want to check new parts of your code, new features, more meticulously. And if you suppress warnings on old code, they won't be issued again, but you can return to them later. And you're going to refactor it at some point, right? And when you do that, the code will change, and all the warnings you suppressed before, they will naturally go away, and you will see only the new ones. Yeah, so it's a good idea usually to disregard really old code in terms of analysis. Okay, let's talk about some extreme cases. Of course, we have here a lot of people from embedded, I believe, and I was going to talk about Misra, which is widely used. So forgive me in advance if I say something, I don't know, offensive. But Misra, it might be good for specialized software, but if you don't design your project around Misra standards, you will probably be surprised by the way your error report looks if you run an analyzer which supports Misra. That's why in our tool it's off by default. It's off by default to prevent situations like this. This is a screenshot from Visual Studio. It's not the biggest project in the world, but it was never designed for Misra. And as you can see, there are 40,000 errors issued by Misra alone. So if you do it carefully, it may work, but in most cases, some parts of tools you only need if you design your software in order to accommodate them, some diagnostic rules. Well, it's not that extreme, because even if you're not writing for an embedded car software or something, you can still use Misra. If you just use a subset of its rules, like for example, you can easily enforce some code style on your team with it. Like, let's say you have a rule that every block of the if statement should have curly braces, and it's difficult to find things like that by just looking at code, but the tool can act like a linter and tell you, okay, this code style is wrong. If you are writing for an embedded system and you use Misra, you won't probably have issues with it because your code is probably compliant. Okay, what else can static analyzers do for you? And that's kind of funny example, because you probably know that there are licenses which propagate themselves to all parts of your software if you use a file which uses them. So some of them are viral, and if you are not going to, make your code open, you should be really careful about using someone else's code and violating their license terms. And You may do it even unintentionally. For example, someone on your team includes some file which is licensed under GPL. But good news, you're covered because it's findable by automatic means. And well, we have the diagnostic rule like that. If we see this GPL header, we can warn you. Okay, so we are at the end, more or less. Let's just summarize, act like a scribe here. So it can be difficult to deal with an old project, but it's possible if you do it carefully. Uh, and for new projects, you just have to do everything just to keep your code from becoming a mess from the beginning. And you just need to be careful about legacy if you are dealing with something old. Analyzers, different kinds of them, can make it easier for you, and I highly recommend using them from day zero, basically, when you start doing something. Automation is good. I think it's obvious. Well, that's all from me. Have a good day, everyone. Thank you for coming.